Okay, so that was clustering algorithm. And that's again a very, very general algorithm, which is used for image segmentation. Now, how we can use that for image segmentation? It's the same analogy we see for like how we do k-means to slick. We'll do the same thing here. Your pixels are actually your sample points, and you can use like the color values. And of course, you have the location. And then within your image, again, you will do random initialization of all those kernels. You will have some kind of search window. And for each search window, you will just repeat those steps. And of course, in this case, one interesting aspect is you can actually run those two steps in parallel for all the initialized points. There is no dependency. And once each point is converged, later you can easily merge points which are actually converging to the same mode. Okay, so that makes like the algorithm very efficient as well. So, and again, this is showing one simple visualization how you can find like different modes, right? And this is again from the image which I showed you earlier. This is just like a 2D projection of that 3D space. And this is along with the colors. You can see like yellow color over here, then blue, then pink. Okay, and how each of these colors is actually trying to get like separate modes. And these red dots are like the identified modes using mean shift. So here you can see that in this like hilly visualization, the higher the point, the denser that point is. And you can see that it's very dense over here, right? So this high density region is actually reflected by this part over here. And at the top is like your mode. And you can see that peaks of like these distributions is actually one of the modes. Okay. Now let's quickly look at like some sample images, how mean shift gives you segmentation. So this is the input image, and you can get something like this. Okay, so this is just showing like different colors, and you can see like the whole green patch over here was detected as one segment, which is quite different from the result which we expect from a slick kind of algorithm, right? So one interesting difference between mean shift and slick is slick will give you like irregular shaped segments, those superpixels, right? So the size of those superpixels won't change a lot. More or less, it will be similar for different segments. But that's not the case with mean shift. It will depend upon like how big the object is. Okay, you have stone like this, which is pretty small, but you have bigger segments as well. Okay, so again, this is a very nice visualization of a mean shift. So this is a colored image, and these are all RGB points visualized like in the 3D space. Now you can see that when mean shift was operated over this, you will find like different modes there, right? And that's exactly as shown in the bottom figure here. So you just converted like, this is kind of, you're trying to discretize your pixel values. Okay, so in this case, you have just this flat red, but in this case, you have variations of red, right? But when you make that flat, you just get one segment here. And again, this is a pretty nice example from real world image, right? It's very noisy, but still that algorithm is very, very robust. And you can see like how different modes are actually converging. So you started from different locations. So for some points, it converged pretty quickly, but for some points, it's still trying to converge. Okay, so now we are done. So you can see like this is kind of several iterations, maybe 80 or 100 iterations. And then the idea is like wherever these pixels were actually moving when we were converging, all of them actually belong to that particular segment. And you can get like with that kind of convergence, this is the result you will get. Maybe you can see like pretty decent, right? Some of the text is actually also segmented. Okay, so the good thing about mean shift is we don't need like any estimation of how many clusters we have to how we have to we have to determine, right? It will do it automatically for you. And it doesn't matter like how many modes you have in your color. So for example, some images might have just 2 modes or 2 segments. It will work in that case as well. Some images might have hundreds of different segments. It will operate in that case as well. And very robust to outliers, because you can see, because we are trying to compute like mean over a larger area, right? So even if we have some outliers as pixels, I think they will be easily filtered out. And we only need one parameter, which is like the window size. What should be your search size, and which is kind of reasonable because you know that how big your segments should be. So depending upon that, you can easily set that window size. Okay, some of the drawbacks, not drawbacks, but again, I will say properties. The output will depend highly on the window size, and that's fine. It's computationally expensive because again, it's iterative, and you can imagine like each step you have to compute that mean. Okay, and depending upon like how many initialization points you have, you'll have to do that for all of those points. So the idea is like if you have very high dimensional data, so for images, it's fine. If you're just using like, let's say the colors of the position, it's 5-dimensional vector. But if it's high dimensional space, for example, 1000-dimensional space, it can be very, very computationally expensive. So not easily scalable.